Hi guys, my name is Paragpal and welcome back in the new numerical of RCC Design. In this numerical, I'm going to discuss a detailed numerical of one-way slab. From start to end, we will be discussing the numerical with a proper solution step by step with the reinforcement detailing sketch. Okay, you can read these notes from my website. Okay, so link of this notes are given in the description box, but you can also visit my website www.civilnotes.com. Okay, this is very important website for all of you, and if you visit on this website you will get lots of all subject notes for your easiness, right? So let's get started. So first of all, we have one very detailed numerical which might come in examination always. Okay, so let's go through that one. A one-way slab is designed for effective span of 3.3 meter. It means we already have an effective span. Okay, the superimposed load including 4 kilonewton per meter square. Now we have a load of load, and that is a superimposed load. Okay, taking modification factor 1.2, we have a modification factor, right? We need to design the slab, and with slab we need to design the one-way slab. Okay, that's very important thing. Also we need to sketch the cross section of the slab, which I just shown you right now, showing the reinforcement detailing. Use M20 grade of concrete and Fe 4 and 5 steel. So this is the basic numerical. There's a lots of information given and we are good to go to solve this numerical. So see what is the given data. We have a span of 3.3 meter. We have a lie load and floor finish of 4 kilonewton. See, whenever there is a superimposed load mentioned, remember you got lie load and floor finish, which is 4 kilonewton per meter square. This is really important thing. Now you have modification factor of 1.2. Now this was the basic detailing is available with us. Now let's understand that what are the steps we need to follow. So first is we need to follow to design the constraint. What are the constraints we need to design? That's very important thing. So in our numerical we have M20 grade of concrete and Fe 4 and 5 steel. So yield strength of steel, which is Fy 4 and 5, is available with us, right? Characteristic compressive strength of concrete, which is FCK 20 kilonewton per mm square. So these both two things are coming from here, right? There is no any extra exercise we have done. Understand? So let me just remove all these things so you can get these things properly. Now let's understand the maximum depth of neutral axis, which is XU max. Now this is not given in the numerical, but this is a standard. So the maximum depth of neutral axis is calculated by 0.48 into small d, which is effective depth, and ultimate moment of resistance, which is ME limiting, is calculated by 0.138 FCK BD square for M20 and Fe 4 and 5 steel. Okay, so these are the two things which is irrelevant, which is relevant for Fe 4 and 5. Okay, if it is Fe 500, this scenario will be different. Understand? Now for this I can refer you some things, okay, some details explanation, so you can refer that one. Now, so first step we completed to identify the design constraint. Now the second step is you need to estimate the slab thickness. Before the design of the slab, what will be the slab thickness is very important, and that is calculated by the formula D equals to span divided by 20 multiplied by modification factor. Now you have a span of how much? 3.3 meter. So let's convert the span in 3300, and this is in mm. Okay, 20 is a standard and 1.2 is a modification factor. We have this modification factor over here. Okay, so after providing all the value, we will get the depth or the slab thickness as a 137.5 mm. Now let's assume that we are gonna providing 10 diameter of main bars and nominal cover of 20 that we are considering ki okay, we got the thickness. Let's understand that we are going to provide the 10 diameter of main bars and a nominal cover of 20 So to calculate, this is a effective depth. Now let's calculate the overall depth. So to calculate the overall depth, what we have to do is we need to do the d equals to small d plus what is the cover we are going to provide plus diameter of bar, okay, divided by 2. So this is our total slab thickness, right? These are our bars, okay, and in between of this we are going to provide definitely the cover. So the overall depth is calculated by the 137, which is a small d, plus this cover, okay, the clear cover, okay, which is a 20, plus what are the bar, and we are providing cover in middle of that. So the bar diameter is 10 divided by 2. So it will gives us d equals to 162.5. Sorry. So let's assume that 162.5 become 165 So the total overall slab depth is become, the overall slab thickness will become 165. Okay, so that will be the total depth. Okay, now let's understand, like this is a total d comes into picture. Now what understanding is what would be the available effective depth. So from this, now we got the total depth. Now from this we need to calculate small d. You understand? So we have a capital D. First we calculate the small d, then from that we calculate capital D. Now again from this we need to calculate the again small d. Okay, so sorry, so that is calculated by capital D minus clear cover minus 10 by 2. Same process we have to do. So this figure will change and this will comes to this figure. Okay, so what will happen from this, whenever you do the quantity takeoff, okay, quantity calculation, it will change, right? So 140 and 137.5, there is a huge difference in that whenever do the quantity calculations, right? So it is very simple that we follow this phenomena, that we first calculate the effective depth. Okay, sorry, we first calculate the effective depth, then we calculate overall depth, and then again from this we are calculating again effective depth by minusing the clear cover of 20 So 165 minus 20 minus 10 by 2. So we got 140 Okay, now this is the overall depth we got. Okay, this is the overall depth. Now let's understand the effective span calculation. Now we have an effective span of 3.3 meter as a given. Okay, so this is the third step. Fourth step is load calculation. So we are considering 1 meter wide of strip. So if you design the slab in ETABS software or in STAT software or whichever the software, you need to create the strips to design the slab. So we are considering that the 1 meter of wide strips, okay, across the slab. It means this is a slab, okay, and you are considering one strip here, one strip here, one strip here, one strip here, like this, one strip here on this direction. So you are putting the load on these strips. Okay, so you are putting the load on these strips, load on the strip like this. Okay, so this is the process to do the design of the slab. So this is what the process actually we do as a structural engineers, right? So first of all, what we have to do is we need to calculate the load calculation. So what would be the self weight of the slab that we need to calculate? So self weight of the slab is Very simple. 1 by 1 meter that we are consider the white strip, 0.165. Okay, why? Because 0.165 is the total depth multiplied by density. Okay, so you got 4.125 kilonewton per meter. Now weight of floor finish and live load. So we already have 4 kilonewton as a kilonewton per meter as a superimposed load into 1 by 1 meter as a white strip details. So it is 4 kilonewton per meter. So what would be the factored load? So the addition of 4.125 plus 4 is 8.125 kilonewton per meter, and multiply this by 1.5. So to calculate the factor load, you need to multiply the total load, okay, which is a self load, okay, the self load and the floor finish and lie load, okay, by 1.5. So 4.125 plus 4, which is become 8.125, multiply with 1.5, you get the value of factored load as a 12.1875 kilonewton per meter. So this is a load that we are going to use, okay, for the design. My bad, sorry. Okay, this load we are going to use for the design. Right now, next step number 5, factored, it means maximum bending moment we need to calculate. How we can do that? So for that, there is a very simple formula we have, which is factored moment equals to factored load into effective length square divided by. So we have a factored load of 12.1875. Effective length we have, which is given for us, which is 3.3 meter, divided by it as a standard. So we got a factored load as a, here we have 16.59 kilonewton into meter. Remember, load is per meter, movement is into meter. Okay, now the next step is we need to calculate overall depth and effective depth now, because from that, whatever the overall depth we calculated, which is 165, and the effective depth is 140, whether these are the correct or not, because whatever the calculation we have done from the length till the movement, okay, is along with this database, capital D and the small d. But is it aligned with respect to our movement that we have calculated or not? That we need to understand. So that's the reason we need to understand what is the requirement of the depth based upon the load. So we are going to equate limiting moment equals with respect to the factored moment, what we calculate. So the limiting moment for the, at the second stage, I calculated that here itself 0.138 FCK into BD square for FE 4 and 5. Okay, so ME limiting is 0.138 FCK into BD square equals to MD. So 0.138 is standard, FCK is a 20, B is a 1000, like 1 meter. Effective D we need to calculate. Okay, now MD we already calculated 16.59 kilonewton into meter, but this is in Newton, so we need to multiply this with respect to 10 raised to power 6 to make it a Newton. Okay, now if you put this detail in the calculator, or it's very simple guys, you need to just bring this database at the below in the division, okay, and take a square root of this. So you will get the value of effective depth as a 77.53. Okay, that's very simple. You can just put in the root, put the data 6, okay, and that's very simple for you. Okay, now so see effective depth, what is required will come into as a 77.53. Okay, if you're not able to solve this one, please let me know, I can able to help you out. So D equals to 77.53 comes into picture. What does it mean? So available depth is equals to 140. It means this moment we calculate, the factored design we calculate with respect to 140 mm. And what is the requirement? The requirement is 77.53, which is lesser than this 140. It means our design is okay. We are correct for the design. Whatever the data you have considered, it is proper and it is correct. So we can provide the overall depth as a 160 mm and the available depth as a 140 mm with the clear cover, whatever the difference of all these things. Okay, now with respect to this database, okay, with respect to this data, we need to calculate the how much steel is required for the design of the slab. So there is a very simple formula. AST equals to 0.5 FCK upon F5 in bracket 1 minus under root of 1 minus 4.6 MD divided by FCK BD square into BD. So this formula every civil engineer should know. So you have every single value. You have FCK as a 20, you have F5 as a 4.5, you have MD as a 16.59 into 10 to the power 6, FCK as a 20, B as a 1000 and D as a 140, which is this one. You have multiply by 1000 into 140, the same figure. So you got the area of steel required is 346.13 mm square. Okay. Now, after getting the area of steel, you need to identify at what space you can provide the main reinforcement, because now let's consider this is your slab area. This is your first steel bar, this is your second steel bar, third. But what is the spacing distance between this? This you need to calculate. Based on that, you can distribute them and you can calculate the number of bars also, right? So to calculate that, we have a formula S10, because why 10? Because we are providing the 10 mm of diameter. 1000 into pi by 4 into diameter square divided by 346.13, which is the area of steel. Okay, so the SD become here, the spacing between the bars is coming 226.91. Okay, so you can, we are considering it as a 225 mm. We can reduce it, but not reduce as very severe. We are taking the nearest round figure. Okay, so we are rounded it to the nearest. We can make it also as a 230 or we can make it as a 225. Okay, so this is the spacing between the two bars, right? Now let's calculate the 3D calculation. So 3D calculation is very simple. 3 into D we need to make. So whatever the dimension of the effective depth, multiply the 3, you got 420 mm. Okay, now what is the minimum spacing? Minimum spacing is a 300 mm. Right, that is what we require. So based on that, let's calculate what AST we are gonna provide. So AST provided is means that 1000 into pi by 4 into diameter square upon 225, and 225 is nothing but a spacing that we have calculated. So it means we are gonna provide a AST of 349.06, and whatever we calculate 346.13. It means that our area of steel is perfect. So 349 and 346, we are nearest, we are equivalent to the related area. Now let's identify area of space of distribution steel. So first of all, AST minimum is nothing but 0.5% into B into D. It means 0.15 divided by 100. B is 1000 and D effective day is at 165 mm. So it becomes 247.5 mm square. Okay, now let's identify the spacing of diameter that is given by the formula SD equals to area of 1 bar divided by AST minimum into 1000. So area of 1 bar is very simple guys, pi by 4 into 6 divided by 2 square. Okay, so we got 28.27. Why? Because we are providing 6 mm diameter of mild steel distribution bar. Okay, so 10 mm is different, this is a distribution bar. So for this we also got the spacing is very simple, that whatever the data 28.27 divided by the distribution steel area 247 here. So we got spacing as a 110. So we have a main bar, we have a distribution bar, both. Now let's check the allowable spacing. So allowable spacing is checked by 5 into depth. Okay, so 5, what is the depth? Effective depth is 140. So allowable spacing is 700. And maximum spacing we can provide as a 450 mm. So the minimum spacing we can calculate it as a 114 mm, approximately 110 mm. That's what we can do. So we can go for this one only. Okay, so let's provide. So this is the reinforcement detailing we have. So the conclusion is we can provide 6 mm diameter distribution bar at 110 mm center to center. Okay, so this is a total reinforcement, this is the effective length, guys. Okay, these are the main bars of 10 dia. Okay, and these are the distribution bar of 6 dia. Okay, so see, we have calculated this one, okay, as a main bar. Okay, and this one is as a distribution bar. Okay, right, you got that. So this is a spacing, this is a reinforcement detailing. Okay, you can see it properly, right, and this is a cross section area. So based on this diagram, you can solve your problem and you can easily get good marks in the examinations. I hope you like this video. Okay, don't forget to visit my website, because this website is very important